concept of steric number is very useful because it tells us the number of hybridized orbitals that we have. So to find the steric number, you add up the number of sigma bonds or single bonds, and to that you add the number of lone pairs of electrons. So let's go ahead and do it for methane. So if I wanted to find the steric number, right, the steric number is equal to the number of sigma bonds. So I look at around my carbon here and I see 1, 2, 3, and 4 sigma or single bonds. So I have 4 sigma bonds. I have 0 lone pairs of electrons around that carbon. So 4 plus 0 gives me a steric number of 4. In the last video, we saw that sp3 hybridized situation, we get 4 hybrid orbitals, and that's how many we need. The steric number tells us we need 4 hybridized orbitals. So we took 1 s orbital and 3 p orbitals, and that gave us 4 sp3 hybrid orbitals. So this carbon must be sp3 hybridized. So let's go ahead and draw that in here. So this carbon is sp3 hybridized. And in the last video, we also drew everything out, right? So we drew in those 4 sp3 hybrid orbitals for that carbon, and we had 1 valence electron in each of those 4 sp3 hybrid orbitals, and then hydrogen had 1 valence electron in an unhybridized s orbital. So we drew in our hydrogens, right, and the 1 valence electron like that. This head-on overlap, right, this is of course a sigma bond. So again, we talked about this in the last video. And so now that we have this picture of the methane molecule, we can think about these electron pairs, right? So these electron pairs are going to repel each other, right? Like charges repel. And so the idea of VSEPR theory tells us these electron pairs are going to repel and try to get as far away from each other as they possibly can in space. And that means that the arrangement of those electron pairs ends up being tetrahedral. So let's go ahead and write that. So we have a tetrahedral arrangement of electron pairs around our carbon like that. When we think about the molecular geometry, so that's like electron group geometry, when I think about the geometry of the entire molecule, right, I could think about drawing in those electrons, those bonding electrons like that. Right, so we have a wedge coming out at us in space, a dash going away from us in space, and then these lines mean in the plane of the page. And so we can go ahead and draw in our hydrogens, and this is just one way to represent the methane molecule, which attempts to show the geometry of the entire molecule. So the arrangement of the atoms turns out to also be tetrahedral. So let's go ahead and write that. So tetrahedral. And let's see if we can see that 4-sided figure. So a tetrahedron is a 4-sided figure, so we can think about this being one face, right? And then let's go ahead and draw a second face. If I draw a line back here, that gives us 4 faces to our tetrahedron. Right, so our electron group geometry is tetrahedral, the molecular geometry of methane is tetrahedral, and then we also have a bond angle. Let me go ahead and draw that in. So a bond angle, this hydrogen-carbon-hydrogen bond angle in here is approximately 109.5 degrees. All right, let's go ahead and do the same type of analysis for a different molecule here. So let's do it for ammonia next. All right, so we have NH3. If I want to find the steric number, right, the steric number is equal to the number of sigma bonds. That's 1, 2, 3, so 3 sigma bonds, plus number of lone pairs of electrons. So I have 1 lone pair of electrons here. So 3 plus 1 gives me a steric number of 4. So I need 4 hybridized orbitals. And once again, when I need 4 hybridized orbitals, I know that this nitrogen must be sp3 hybridized because sp3 hybridization gives us 4 hybrid orbitals. And so let's go ahead and draw those 4 hybrid orbitals. So we would have nitrogen, and let's go ahead and draw in all 4 of those. So 1, 2, 3, and 4. Those are the 4 hybrid orbitals. When you're drawing the dot structure for nitrogen, right, you would have 1 electron, another electron, another electron, and then you'd have 2 in this one, like that. And then you go ahead and put in your hydrogens, right? So once again, each hydrogen has 1 electron in an unhybridized s orbital. So we go ahead and draw in those hydrogens, right? So our overlap of orbitals, so here's a sigma bond, here's a sigma bond, and here's a sigma bond. So 3 sigma bonds in ammonia. And then we have this lone pair up here. So the arrangement of these electron pairs is just what we talked about before, right? So we have this tetrahedral arrangement of electron pairs or electron groups. So VSEPR theory tells us that's how they're going to repel. However, that's not the shape of the molecule. So if I go ahead and draw on another picture over here to talk about the molecular geometry, I go ahead and draw on the bonding electrons like that, and then I'll put in my non-bonding electrons up here, this lone pair right here, housed in an sp3 hybridized orbital. So the arrangement of the atoms turns out not to be tetrahedral, and that has to do with this lone pair of electrons up here at the top. So this lone pair of electrons is going to repel these bonding electrons more strongly than in our previous example. And because it's going to repel those electrons a little bit more strongly, you're not going to get a bond angle of 109.5. It's going to decrease the bond angle. So let me go ahead and use the same color we used before. So this bond angle is not 109.5. It goes down a little bit because of the extra repulsion. So it turns out to be approximately 107 degrees. And in terms of the shape of the molecule, we don't say tetrahedral, we say trigonal pyramidal. So let me go ahead and write that here. So the geometry of the ammonia molecule is trigonal pyramidal. And let's analyze that a little bit. So trigonal refers to the fact that nitrogen is bonded to 3 atoms here. So nitrogen's bonded to 3 hydrogens. So that takes care of the trigonal part. The pyramidal part comes in because when you're doing molecular geometry, you ignore lone pairs of electrons. So if you ignore that lone pair of electrons and just look at this nitrogen right at the top of like this pyramid right here, so that's where the pyramidal term comes in. So bonded to 3 other atoms like this, this, and this for our pyramid. So trigonal pyramidal is the geometry of the ammonia molecule, but the nitrogen is sp3 hybridized. All right, let's do one more example. Let's do water. So first we calculate the steric number. So the steric number is equal to the number of sigma bonds. So that's 1, 2, so 2 sigma bonds, plus numbers of lone pairs of electrons. So here's a lone pair, here's a lone pair. So we have 2 plus 2, which is equal to 4. So we need 4 hybridized orbitals. As we've seen in the previous 2 examples, when you need 4 hybridized orbitals, that's an sp3 hybridization situation, right? You have 4 sp3 hybridized orbitals. So this oxygen is sp3 hybridized. So I'll go ahead and write that in here. So oxygen is sp3 hybridized. So we can draw that out, showing oxygen, right, with its 4 sp3 hybrid orbitals. So there's 4 of them. So I'm going to go ahead and draw in all 4. All right, in terms of electrons, this orbital gets 1, this orbital gets 1, and these orbitals are going to get 2 like that. All right, so that takes care of oxygen's 6 valence electrons. When you're drawing in your hydrogens, right, so let's go ahead and put in the hydrogen here. So once again, each hydrogen with 1 electron in an unhybridized s orbital. Like that. So in terms of overlap of bonds, here's 1 sigma bond and here's another sigma bond, right? So that's our 2 sigma bonds for water. Once again, the arrangement of these electron pairs is tetrahedral. So VSEPR theory says the electrons repel, and so the electron group geometry, you could say, is tetrahedral, but that's not the geometry of the entire molecule. Okay, so that's just thinking about electron groups and these hybrid orbitals. The geometry of the molecule is different, so we'll go ahead and draw that over here. So we have our water molecule and draw in our bonding electrons, and now let's put in our non-bonding electrons like that. All right, so we have a different situation than with ammonia. With ammonia, we had 1 lone pair of electrons repelling these bonding electrons up here. For water, we have 2 lone pairs of electrons repelling these bonding electrons, and so that's going to change the bond angle. It's going to shorten it even more than in the previous example. So the bond angle decreases, right? So this bond angle in here decreases to approximately 105 degrees, rounded up a little bit. So thinking about the molecular geometry or the shape of the water molecule, so we actually call this bent or angular. So this is a bent geometry because you ignore the lone pairs of electrons, and that would just give you this oxygen here and then this angle, right? So you could also call this angular. So we have this bent molecular geometry like that, or angular. And once again, for molecular geometry, ignore your lone pairs of electrons. So these are examples of 3 molecules, and the central atom in all 3 of these molecules is sp3 hybridized. And so this allows us to, this is one way to figure out your overall molecular geometry and to think about bond angles and to think about how those hybrid orbitals affect the structure of these molecules.